And today I should be able to finish all that. The laptop people can try to get it in. Last one there as well. Emailing home to Mexico. No, okay. So this is where we were. We have this in our own data. We see on the left the distribution of the happiness scores of youth, and only the half, or roughly the half, of people who got the picture here of the correct guy before answering the happiness questions. And there you see a similar distribution on the right for the ones who saw the picture of the funny baby, or the happy baby, as I called it in the variable name. The question is it really the case, and we already see from the means that it's not likely to be true at all, and I see that I copied, in fact, a picture from last year because the actual numbers from this year are slightly different. But the question is, are people happier after they see this than after they see that? And we're aiming for that difference, and that is, let's say, prototypical for examples of the kind. One variable has two categories. In this case, you either saw the left or the right picture, and the other variable is interval scale. And I already showed also that this is in the end what we're up to. So this is a standard recipe that you simply have to memorize. First, if you want to check all this, then we need a couple of assumptions to be checked before we can actually do something. And the assumptions that we need is we have to test for normality. So these two humps that you see over there, you have to check, are these, let's say, normal enough? If not, then we cannot run our standard test. And we will show how to go. The Stata commands that go with it are called swilk and ttest. And what you want is that both will show you that the distribution is, let's say, normal enough. If that is indeed the case, then we're good to go, and we run a ttest through this command, where the y is the interval scaled variable and the x is the variable that is categorical with two categories. However, if not, then what you can try to do is somehow transform that hump that you have over there in some other shape that is more normal than the one that you have. And we'll go through the ways in which you can do this. If that works, great. So if, let's say, the square root of the y variable works, then you create that variable, and you do the same t-test now with that square root y. That's relatively easy. However, it could happen that there is not a sensible transformation you can come up with, and then there are only two things left: a so-called ransom test and a median test. And then that's pretty much all that you have. And then you sort of hope that all these different tests turn you in the same direction. What you don't want is that here you find the difference for the ransom test and here you don't, but it might happen. And we'll see how that goes in a minute. Okay, this is another one that I showed way at the end last time. This one was relatively easy in the sense, well, H0 is easy to understand. For 0.5, there we came up quite easily with a number. We simply count how many times we have heads out of 1,000. And that is a decent statistic to figure out if what we actually have is a fair coin, if H0 is likely to hold. There you can actually do this ourselves if you want, or simulate the whole process. That would work as well. Here it became already a little bit more difficult. We have two tables, two cross tables that we want to compare. One is the cross table with all the expected frequencies in there, if the rows and the columns are independent. And the other one is the actual table that we have. And for that we needed sums of squared differences, and needed to believe that at least approximately that has a chi-square distribution. I told a little bit about that, but not a lot. The only thing is the same principle applies. We know the distribution of that statistic. That statistic was the sum of all these square differences. We can figure out if what we get in our data is weird, given that the rows and the columns are independent. And here, there is even more hand-waving involved. Here I said, well, first let's start with that we compare here two things that themselves are normally distributed. That's already quite a big extra here that we need. And then let's see if we can find somebody else who can come up with a decent statistic that we can use. We have that, it's called a t-statistic. And in the t-statistic are two things. And one is the difference between the midpoints of these normal distributions. How far away are these? That's the thing on top. And the other thing that's there, that looks complicated, that has to do with how wide are these humps. The tighter they are, the easier it is to conclude that there is a difference. And for that, yeah, these kind of things we'll do a couple more times. Because here you have it. First, that more complicated thing, where the t-statistic is, you simply memorize loosely what it is. It sort of looks like a normal distribution, so you could think of the same shape actually in this case. And if you would have paid really close attention, then you could argue here, well, it's actually kind of weird that we now want to start with two normal distributions because we had the central limit theorem, and the whole idea of that thing was that if your sample is large enough, then, loosely speaking, you get something that is normally distributed. Well, that was the fuzzy way of saying it. Actually, what you have is, if n is large enough, you can get arbitrarily close to a normal distribution, but it's not clear when n is large enough. And we know, for this case, when we compare two groups on an interval scale variable, that very often, if we simply hope that the central limit theorem will do its magic, that this is not good enough. So here we make it, let's say, a little bit easier on ourselves, and we're only going to do this if we can reasonably assume here that the empirical distribution that we have in our sample is close enough to normal. Okay, so that we need to have, and actually also what we need to have is, making it still easier, is not only that both of these humps are normal, but also that the variance of these things is the same. So if you have a hump that has this shape and a similarly shaped hump but it's lying over there, okay, perhaps then we can do the actual test. How likely is it that there is a real difference in the population? That's actually also something that we need to test. More about this in a minute. Okay, so the rest is all the same. Stata will produce a statistic. Stata will produce that number t, and Stata will also produce a value that we can compare it to 5%. If it's below 5%, we reject H0. If it's above 5%, H0 is supported, where H0 is that both groups have an equal mean. Okay, but now we get into a bit of an issue. We need a test before we can actually do the test. So we're comparing two groups, and before we can do it, we first have to test something else, namely that within these two groups, the distribution is normal. Now, how do we do this? Well, this is the point where we have to start getting used to that we're not bothering at all anymore with what that statistic will actually look like. Somebody else has thought of this. It's way too complicated to go into all the details. I'll show you the details in a minute. But these are the ideas that are being used. ttest and swilk, both will test for normality. The first one is relatively easy to understand. We know that a normal distribution has a skewness of 0 and a kurtosis of 3. So, if we look at an empirical distribution, one thing we could simply calculate is, well, what is the skewness of this distribution? Is it 0? And what is the kurtosis of this distribution? Is it 3? And if it's far away from these numbers, it's not likely to be normal. The intuition behind that is relatively clear, although it's not clear just yet how far away really is too far away from normal. That is where we need the statisticians for. And the other idea is from two people called Shapiro and Wilk, already from 1965. There the idea is a little bit more elaborate. For sk-test, you only look at these skewness and kurtosis. For the swilk test, what you do is, well, basically the intuition behind it is, if the shape of a normal distribution is like that, and I draw the shape of the distribution that I have, and I compare it to the actual line there that I find, then if it's normal, it's likely to be close to the line. And what we're measuring is how far away it is from the line, loosely speaking. If it's too far away from a normal distribution, it's not likely to be one, and that is what we're testing twice. Okay, so, yeah, none of this we are going to mess with, because this is really relatively complicated stuff. And just to show you that it is, okay, here we see, let's check. There we have the test of skewness. To test for skewness, we have this as a test statistic. Okay, not very intuitive anymore. But somebody has figured out that this is a good idea. Good for us. For kurtosis, if we wanted to test it separately, we have another statistic there, Z2. Equally complicated, I would say. And in fact, what we want to test is something where we do the skewness and kurtosis in one, and that's possible too, because k squared over there equals to the sum of the squares z1 and square z2. That in itself has already an approximately chi-square distribution with 2 degrees of freedom. Forget about what that exactly means if you got lost in the chi-squares. The point is, we can calculate this statistic, and this statistic has a known distribution if the original empirical distribution would be normal. So if our distribution would be normal, we know what kind of values that number would take. And that is what you will see happening. Well, you won't see it happening, but what will happen behind the scenes in Stata. Okay, so here, this is what we have, is if H0 is normal, we get a statistic, Z1, we know what it's like. If H0, again, is that the distribution is normal, we have a statistic Z2, and then we have another one that we can test with. Okay, actually it's slightly more complicated. That is a decent test, but what Stata does is come up with an improvement of that test that is now standard in literature. So Stata actually does something slightly more complicated even, but luckily none of that you'll notice. This is the only thing you'll notice. That's actually relatively straightforward. The command is ttest happy, that's the happy variable that we have, if happy baby equals to 0. What we need is normality for both of the groups. So you don't want to test the variable happy as a whole, but only for that group separately. Here for happy baby equal to 0, there for happy baby equal to 1. You get separate tests for skewness and for kurtosis, but these you can simply disregard. What we're looking for are these numbers over there. And what we hope to find here are numbers that are above 0.05. Values above 0.05 over there, then we support normality, or stated otherwise, we do not reject normality, which is great because then we can run our standard ttest command and we need not do anything that's more complicated than that. It is a bit crude, of course, because the only thing that we're looking for is, okay, skewness is equal to 0. That simply meant that the whole distribution is not tilting to one or the other direction. And obviously there are many different distributions that you could draw that have a skewness of 0, but do not resemble a normal distribution at all. And the same goes for kurtosis, but, you know, at least it's one way to go. And this is the other one. I'm showing this plot because in many other statistical packages, by the way, also in Stata, but for instance also in FPSS, you can get plots like this, where the idea is that to figure out if a distribution is normal, or let's say normal enough, what you do is you eyeball the plot, and what you're expecting, no, not what you're expecting, what you're hoping to see is that all these points here are on the line. So this would be something that came from a normal distribution, and this would be something that, yeah, and now we have to think about, is this on the line enough or not? That's a bit of the problem with the eyeballing of these kinds of graphs. It's not obvious that this is close enough to the line or not. But still, what you could see, for instance, is something like this. If you would have a uniform distribution, so a flat line, and you compare that with a normal distribution, obviously that's not going to fit very well. Then what you'll see is at first, these dots are above the line, then they are somewhat close, and then they are below the line. So this would typically be, let's say, visual evidence of that the empirical distribution that we have is certainly not normal. What that swilk test does is, behind the scenes, calculate a test statistic for these kind of things, so that you don't have to look at the plot and try to figure out if this is close enough to the line or not. This is how it goes. Swilk happy if happy baby equal to 0, swilk happy if happy baby equal to 1. And what we see here, well, it's the same result as the SK test. Both are above 0.05, but it was pretty darn close there. So this is good. We're good to go with the ttest command. Yes?
Should you always run both swilk and the SK test?
Yeah, in principle, I would say yes. Because in principle, what you would like to, what all these tests do is they test part of the normal distribution. So skewness and kurtosis, only one part. That shape, actually also only one part. So in principle, given that we have these two, these ones both should work.
Okay.
It is a bit of a dangerous answer in the sense that there are way more normality tests than just these two. And the idea would not necessarily be to do all 45 or something, but for two, it's likely that you'd like to find here that it's all okay. One reminder in between the ttest commands in a minute will have something like this: ttest happy, comma, by happy baby, and that'll work. And it would be nice to be able to do this also for these kind of commands. So swilk happy, if happy, you have to write that out completely. Would be nice if you could say something like swilk happy, comma, by happy baby. Would make sense, sort of, but it doesn't work. So just if you at some point get that this is not what was actually working, you need to write the if statement behind it, and then it will. Okay, let's see. Yeah. Now the part where we sort of deviate from many standard statistics books. In many of these standard statistics books, what you get is first you have to test for normality. Okay, that we just did. And you have to test for equal variances. So you have to test that the width of that hump is equal across the two groups. And we've done this for years, and many people still do. And in a minute, I'll come up with the argument that we won't do this in this case. However, if somebody forces you to do it, then it's possible, because there is also a test for the equality of variances. It's called SD test, for standard deviation. Standard deviation is the square root of the variance. So that will work like this, as the test of that happy variable by happy baby. What you get here is a comparison between these two groups, as we had it before, and you get a number over there. That number in the middle you have to look for. The number here is 0.01, which is below 0.05. H0 is something with equality. In this case, the variance of the one hump equals the variance of the other, and we reject that. So in this case, H0 is rejected, and officially we should do something else. Now, luckily, this is easily solved if these variances don't work out so well, because the t-test has an extra option to add right there, called unequal. So this is what you do standard if the variances are not the same as we just found it. And the difference compared to many of the statistics textbooks is that by now, typically what you should do, according to literature from nowadays, is simply run this all the time. Even if you would find that these variances are the same or similar enough not to reject H0, then still type the unequal behind it. This gives, in general, more appropriate results. And testing for the differences in the variances is not necessary at all anymore. So this is easier actually than what most people do. There is no need to really test for these equal variances. Simply assume that they are unequal and add that as an option to the t-test command. That'll work. Okay, so the list of assumptions is a little bit easier. The first one that was okay to begin with here, and the second one that we typically see in many statistics books we disregard. Okay, so in that case, we simply could type the t-test command. Oh, I have to peek here just to see what came out. It was pretty obvious what came out because the means were so close already. What we see here, look at that number over there, 0.37. So in this case, H0 is not rejected. H0 is the mean of these two groups is equal, and we don't reject that. So we do not see any evidence for that the happy baby picture delivers anything else than the depressed guy picture. Yeah.
Why are we still allowed to use t-test if the variances are
First of all, if these variances are unequal, then still you're allowed to use the t-test. The only thing is that you have to take into account that you have this extra option over there. So you have to tell Stata that there is unequal. And it is even easier than that, because since, let's say, 5 or 10 years or so, we know that it's actually better to forget about the whole testing of equal variances and simply type this always. Not good enough?
You're comparing two meters, right?
Yeah.
And you're comparing whether or not this is really different.
Yeah.
But if the variance, if you have one with a small variance and one with a large variance, it's harder to tell whether it's really a difference, right? So if you ignore the fact that it may be unequal, then
Yeah,
it's a t-test.
that would indeed, I agree with all of that, but that is not what we're doing. So we have, okay, if you have one normal distribution like this and one normal distribution like this with a very wide variance, okay, that makes a difference. You have to take that into account. In fact, you do. By always having this unequal, since they're unequal variances. Now we have the case where they are actually the same, so like this and like this, so same shape. And the thing that we found, let's say in the last couple of years, is then still we get more appropriate results by assuming that the variances are unequal. So we're not messing with the tight versus wide at all, but instead do what we do then also when these variances are equal. Okay, so this is the testing of the assumptions, and here it worked, and we could do the t-test, and more or less we would be done. But we'd like to get an example too where it didn't work out, just to see what we should do then. Well, okay, let's assume here that we have that the interval variable is not normally distributed in both groups, and what do we do then? And I have an example of that basically on the same variables, but then on the data from last year. If you look at the data from last year, it turns out slightly different. Here you have from 2015, again that normality test. Let's see if I can, does this work? Okay, there you have it now for one group, this one, we have a value that is below 0.05. So now we're rejecting normality for that first group. So this is not working. And what we're trying to do now is first try to transform that shape in such a way that, you know, first it didn't look very normal, and now it does look normal. We take the square root, take 1 over the variable, we take the square of the variable, what have you, and we give that a try. And luckily this is an automatic process in Stata through a command that's called ladder. Here you see it. Oh yeah, here we have the, once more, the if happy baby equal to 0. This is the case where the normality was violated. And here you see the execution of the ladder command. Ladder happy if happy baby equal to 0. And what happens here is that several transformations of the variable are tried. One at a time, and the actual test that is being conducted over there is the SK test. I would have liked to see the swilk test, but nevertheless we have the SK test over there. And what we'll see here first is, well, a cubic transformation, so happy raised to the power of 3, that doesn't help us much because this rejects normality as well. Okay, so it was a nice try, but it didn't work out. Then the square, happy squared. Okay, chi-square value that is a bit lower, but still, we reject normality. So another nice idea, but also didn't work. This one we already had. This is the thing itself. That didn't work. We knew that. The 0.013 is exactly this one. And here you see that in principle there are quite a few more transformations that Stata is willing to try, but in this case didn't do. So let's try to figure out why that might be. Well, this was what the happy variable looked like in this case, and you see here that the minimum value is minus 0.7, and the maximum is 2.5. So we know that this is below and above 0, and in all likelihood that 0 is also in there every once in a while. So that will certainly mean that, for instance, the log of happy won't work, and 1 over the square root also won't work, and 1 over happy squared also won't work. So I first created something else where I added 1 to the variable. I called it happy pulse for positive. So I add 1 to something that is at its minimum minus 0.7. I'm quite sure to end up above 0. And then give that another try with that same ladder command. Okay, let's see. Now I try ladder happy pulse, the other happy variable that I just made, if happy baby equal to 0. And now we get quite a bit more here. Let's see. That one with the orange square around it seems to work. So happy pulse And now we also check the same one for happy baby equal to 1, because if I want to transform the variable, then what I can do is do this in group 0 and in group 1, but what I cannot do is use one transformation in group 0 and use another in group 1. So I have to use the same for both. And in fact here, we're lucky because happy pos squared also rejects normality. So this is good. We now have an extra transformation that we can think about, and in fact it's also the only one, because here you see that all the other ones don't help. They're all below 0.05 except for this one. And here the only other one that we had was the identity that was over there, and that one didn't work. We knew that. So this is solving what we want to achieve here. We take first happy, we add 1, and then we square that thing, and that we know has a distribution that we cannot distinguish from a normal distribution. Questions about this? I see people frowning here and there. Yeah.
Is this data manipulation? Is it
The question is this data manipulation? And it is just. That's the whole thing we do in this course. We manipulate the data. Do you see any ethical issues? No, the only thing is that what I'm trying to achieve here is that instead of the original variable, I try to come up with an other one that fulfills the assumptions here. That's the only thing. Yeah.
Go back to the part where you add 1.
There.
You do, and when you do further analysis, you always use the new variable.
Well, first of all, I'd like to be able to compare the two groups, so I'd like to be able to run the t-test. And then in the end, you'll have to figure out if you want to use that same variable for all subsequent analysis. And as we will see later, it's not always necessary to use that same variable for all subsequent analysis. For instance, in the end, when we do multiple regressions, the assumptions that we need to check are not related to this, but to something else. So it might very well be that if we do another kind of analysis, we don't want to use this transform here. Well, not happy pulse actually. This is what we tried just to make sure that all the transformations that Stata will try will work. And then if we look at what works is happy pulse squared. So the new variable we're making is happy plus 1, brackets around it, and that's squared. That thing cannot be distinguished from normal. Other questions? Yeah. Yeah, well, not for the t-test. If you want to compare these two groups, then this is what you stick to. If you want to do something else with the data, we'll do that later. Then there are other kinds of assumptions that you need to test, and it might very well be that you then need not resort to happy pulse squared and can stick to that happy curve. Other questions? Okay, so here we actually do this. I'm generating happy pulse squared as a square of happy pulse, and I do the t-test. Here I forgot to type the unequal. Okay. So unequal should have been there. Yeah. In any case, here we see a value above 0.05, so equality of the means is not rejected. So the conclusion, as we had it before, doesn't change. We are now, let's say, officially allowed to run that t-test because this variable over there is, let's say, normal enough. And then we see that there still is no difference. So in terms of the answer, it doesn't make any difference. Okay, yeah. Now, something that you have to take into account here. Which kinds of transformations are allowed here? Well, not all of them. For instance, let's say 1 over happy squared. Let's say that we do not have any happy values equal to 0, then 1 over happy squared is well defined everywhere. Okay, so you could think that might be a reasonable transformation. But in fact it is not. All the transformations that are allowed should maintain the order of the cases in your data. So if you have cases 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, only positives, then if you take the squares, then the order of these cases is maintained. However, if you have positive and negative values, let's say you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, And also, minus half, minus 1.5, minus 2.5, then if you take the squares there, then these squares end up right in the middle of the positive numbers that you have over here. So the distribution that you're going to get mixes up the cases in your data. So this is also why it's very often a good idea either to stick to only the transformations that do not do this, or, which is normally easier, simply to make sure that all the values that you have in your data are positive by adding a number.
When you first got the letter, then there also were minuses, and Stata suggested that you put a square do it.
Well, Stata didn't suggest so much. Here, Stata didn't suggest anything at all. In fact, gave nothing back. Exactly for that.
Square and do it in a star.
These?
Yeah, these shouldn't be allowed to do that.
Yeah, sure. So Stata is smart enough, sometimes, but not always. And you need to figure out what Stata is allowed to do. It's up to you. That's the tough part. This is also why I show you this. You have to take care that all this works. Otherwise, Stata will simply assume, I'm not sure why it's necessary, but he wants it, so let's give it a try. And there are some cases where Stata says, okay, this is so weird, I'm not going to do that at all, but it needs not. Okay. Any more questions about this? You'll see very often, is my experience, that if the empirical distribution doesn't look normal at all, not even close, then transforming it won't help so much. So something that is, let's say, looks like a hump but is tilted in one direction, okay. It's possible that you can sort of tilt that back by transformation. Something that looks like this, very, very wild, yeah, you can transform whatever you like, but that's never going to be something that is normal. Okay, so let's suppose that we indeed are in that condition. First try normality, it doesn't work. We try transformation, it doesn't work. Okay, so obviously we do not have a normally distributed variable and we need to come up with something else. And luckily there is a something else. And the first idea is actually relatively crude. What we could do is say the following. It's called a median test. What you could simply check is, well, if I look at the cases in my data that are above the median, and by definition that should be half, and I look at the cases that are below the median, and that's the other half, by definition as well. And then I compare those in a 2x2 table. I can do that basically for any kind of variable. It's quite crude because I simply disregard all the information in the separate cases, and the only thing that I do is, okay, let's look at the first part and the second part, and then let's see if there is a difference in terms of the baby picture versus the sad person, or wherever the variable is that you're looking at, and make that comparison. That comparison I can make, and we actually know how to do it. This is a chi-square test. And the only difference that you have here is that there is a direct command to do this. This crude way of testing. It's called median. Median happy, by happy baby. It splits up the data in two parts, above and below the mean, makes a crosstab, and the chi-square test there. And again, you see H0 is not rejected. There is no proof that there is any difference between the two groups. Okay, so this is chi-squared as we know it. So you could, in principle, do this. And I think I have the example 2 slides down the line by hand as well. Stata is lucky enough to have a standard command for it, but I'll show in a minute how you can do it by hand too. There is one slight complication here. All this is relatively easy if the median is one number in the data, or preferably even not a number in the data, so that the median value is somewhere over here, and indeed half of the data is over there, and the other half is over there. If the median value is, let's say, 5.5, and there are 25 5.5s in the data, then you have to decide exactly where you're going to put your midpoint. Midway in these set of 5.5s, 5.5s to that group, or all 5.5s to that group. You have to take that into account. That makes matters slightly complicated if you want to do all this by hand, because you have to decide then what to do. And this command actually does it for you already. Okay, so, yeah.
So not use a simple chi-square test?
No, you could do a simple chi-square test. Actually, if you wait 2 slides, I'll show you how it works, and then you'll see that this is actually the same. So this is actually what you would do by hand if you would do the whole thing yourself. First, you look at the data here. This is the happy variable again, and you see that the 50% percentile is at 1.25. This is a tab of the same data, and you see here, if you add up these percentages, that here you're crossing the 50. So somewhere between 1.21 and 1.28 is the median value. In this case, 1.25. You could create a variable where you say, okay, you get a 0 if you are over there, and you get a 1 if you are over there. I think I have that example here. Here I do this. Generate a new variable that's called happy_dum for dummy variable, equal to 1 if happy is larger than 1.25 and equal to 0 otherwise. Just to make sure that I do not make any weird mistakes, I add that second command here as well. Missing values are by definition for Stata counted as plus infinity. So plus infinity is certainly larger than 1.25. So for missing values, you would get a 1 in your data here, because missing is larger than 1.25, and I want to make sure that these are not there, so I'll add this line here, replace happy_dum equal to missing if happy itself is missing. And luckily it says here no real changes made, so apparently I didn't have any missings in my data. And now what I do is I type the crosstab of that happy_dum variable I just made with that happy_baby variable, and all the bells and whistles after it that we know from the chi-square test. And here you get your chi-square is 0.439, way above 0.05. And that is exactly the same as what I get with that median command. Find happy_baby, see, the 0.439, and that's not a coincidence. So here you see that, in principle, you could have done all this by hand if you wanted to. And in this case, it was easy because the median itself was in between values. So the real value of the median itself was not a data point in my data. If it is, you have to think about what to do, and that median command does it for you. But in principle, all this could be done by hand as well. But it does sound kind of crude to me, just chopping off half and then comparing that. The other one is slightly more complicated and a bit better. Here is an example where I reduced the data to only 6 cases. Yeah.
Can you use it the other way around as well? So replace chi-square test with a median test? Or a median test with chi-square test? For instance, for 2 variables or variable like we saw.
I think in principle you could. Although I didn't really see why you would want to do it, because if you want to run the chi-square test, that means that you have 2 categorical variables, let's say each with 2 categories, and then just typing tab xy would already do it. So there is no need to type median there. Right.
Is there a coincidence that the basic extract is the same as the continuous corrected?
I don't know for sure, but I think yes. So I don't think that by definition, this, let's see, continuity corrected Pearson chi-square is by definition the same as the 0.536 that we have over there. I seriously doubt that. I'm not sure, but the reason for that is that the whole story that went with the Fisher's exact, we're counting all the different possibilities and we setting them in line and then we check which of these are the 5% that are let's say the weirdest. That doesn't have any obvious relation, as far as I know, with the continuity correction of the chi-square. So I don't think. Well, I'll check, and if I'm wrong, no, I'll publicly admit that I don't. Other questions? Okay, then the other thing that we could do here, let's call a ransom test. I reduced the data here to 6 data points. We have baby equal to 0, and then we have a happy value of 3, 7, and 14, or baby equal to 1, and then we have a happy value of 1, 2, and 4. So this is a 6 data point data set just to explain the rank sum approach on this data. Well, what we could do is the following, and that would be actually a good idea. I have the data over there, have these equal to 1, 2, 3, 4, 7, and 14, that's these values, and the value of baby that belongs to that, 1, 1, 0, 1, 0, 0. And now what I add is a range, simply starting to count from 1 upwards, 1, 2, 3, 4, 5, 6. And what I do is I sum the ranks across the different groups. So what I do here is for baby equal to 0, I see that the ranks are 3, 5, and 6, adding up to 14. And for baby equal to 1, I see that the ranks are 1, 2, and 4, adding up to 7. Now, if baby equal to 0 or 1 is not related at all to how you score on that happiness variable, you would expect that these 1s and 0s are distributed randomly across the whole data set. And that would mean that if you add up the ranks for the 1s and for the 0s separately, that is likely that you get more or less the same number. So what we would like to have here is a test of whether or not this 14 is really higher than a 7, or that could just be a coincidence. And that is what the rank sum test actually does. Again, there's a bit of an issue when we have ties. If we have more than a single value 7, let's say, in the data, we have 8 7s, then what do we do with that rank over here? Who gets to 5 and who gets to 6? So you have to do something with that. And this is how that is done. Again, way more complicated than we need to know ourselves, but here you see there that thing, H0 would be, well, the rank sum of that one group is exactly equal to the rank sum of that other group. And then you can come up with a statistic in the end, right over there, that has a known distribution. And that number that we get says something about how weird the data is, given that H0 is true. And where we, as I said at the beginning, made a bit of a fuss about knowing what that distribution was, here we're simply happily acknowledging that somebody else has come up with that idea for us, and that this is all being tested behind the scenes by Stata. So here's how that goes. Rank sum is the command. Rank sum happy by happy baby. A 2-sample Wilcoxon rank sum Whitney test. Okay, 77 observations in the one, 91 in the other. These are the numbers added of all the rank sums. These are the numbers that you would expect if 0s and 1s would be randomly distributed. And you see here that these numbers are slightly different, but not so much. In the end, you get a test value back. The test value here is 0.34, above 0.05, so H0 is not rejected. Equality of these two groups is not rejected. Okay, now what could happen, of course, we didn't have that here, is that here you find that there is a significant difference. And in the other one, the median test, you find that there isn't any difference. Okay, then it's not that obvious what to do. In principle, because that rank sum test takes a little bit more information into account, all these separate ranks for all the separate numbers, compared to just putting a stick somewhere halfway in the data and then comparing the two groups. I tend to favor that rank sum test, but still, it is a bit weird if in a paper you write something where you have to admit, okay, I find the difference between the two groups, but it's only a bit. I was just wondering about the practical uses of that 1 over square root n rule. What you will typically see, and you'll see it in the Netherlands too, somewhere near March, where we have the next elections in the Netherlands. Well, first of all, we know that we have 150 seats in Congress, and loosely speaking, there is a proportional representation. So that's different from the United States. So in principle, if you have 150th of all the votes, then you get a seat. It's not exactly like that because you have connections between lists and stuff like that. But roughly speaking, this is what you have. Now, what we're measuring, if we want to measure how many seats in Congress you get, is if you have 150th of the votes. And if that is indeed the case, then you can say, yeah, you're likely to get that many votes. The standard prediction, just the number, is not so complicated. If I do a big poll, you get 1,000 or so people. 500 of them say that they will vote for PVV. Then my best estimate is 75 seats in Congress for PVV. Okay? Would it be be such a nice thing, I guess, but statistically, more importantly, you want to say something of the kind, okay, I'm guessing 75, but given the 75 that I guess here, and given the sample that I have, it is plus or minus, yeah, and then what? And near the time that we actually get the elections, or on election day even, typically what you will have is something where RTL4 or just NOS will have a person in the room saying we are doing exit polls. And these exit polls, we make them massive, big enough to be sure about the actual election, given what we find in our sample. We are close enough so that we can say, okay, we're estimating 18 seats for this political party, plus or minus 1 at most. And that's typically the claim that they come up with at that time. If you can double check at some point what the sample size is that they get, you will always see that what they come up with is a number somewhere between 20 and 25,000. And that is not so weird, because that is exactly coming from that 1 over square root n rule. Okay, if you want to be able to make a prediction of a proportion, and that is what we're doing here, plus or minus something, and that something should be 1 seat, and that seat is 1 over 150, then that square root n rule gives you, well, 1 over 150 should be 1 over square root n, which makes n equal to 22,500. So you will get somebody in the studio there who will claim we are doing this exactly right. We are close enough, plus or minus 1 seat for each and every party. And this is why we have polled 22,500 people who voted today. Okay, so that is the statistics, and it's fine. So in principle, this should work, and it never does. You can easily see this happening. For instance, the last time you also saw this. You had people like this, different ones, on 2 channels. And then at some point they came up with the definitive conclusion, their definitive prediction, and already these 2 were widely different. So it's obvious that not both of them could have it exactly right. And obviously the problem that you have here is that all this works, but only, first, if you take a really random sample, and I'm not so sure that that is what they did. It's also not so easy to do. How do you take a random sample of people who come out of a voting booth? First of all, where do you go and stand? That's already slightly complicated. And the other thing is, of course, that if you ask people what they voted, that they tell you exactly what they did. And it might very well be that they tell you nothing, that they tell you something else. And then if you do not have something that can take that into account, yeah, the whole statistics is out the window. You have to do more complicated stuff, perhaps from the people who say they voted P van de A. In all likelihood, 10% actually voted something else, even though they said it to me, because I know this from a previous complicated stuff, and then all the easy statistics is sort of out the window. But in principle, this is correct. You need 22,500, and then you have it right, more or less, by the seat in Congress, at least, that is, if everybody is telling it the way it is. Okay, so, having that off my chest, back to where we were. We went through all the different things that we could do for comparing 2 groups of people on an interval scale variable, and we basically did all the stuff that we had to do there. And that brings us back to the whole recipe that we had. Swilk and ttest, we saw that, testing for normality. If it works, great, run your t-test and assume unequal variances. That'll work. If it doesn't work out so well with the normality test, try a transformation. If that works, great, go with that. If that still doesn't work, use that rank sum or median test, because these always work in the sense that you're assuming nothing about normality whatsoever. Okay, and that begs the question, obviously, well, if that rank sum and that median test always works, then why do we bother at all with the whole stuff above it? Okay, we have 2 that work always and that assume nothing. So why shouldn't we use that one always? And the answer here is, well, when the assumptions are fulfilled, we know that that standard t-test is way better than these rank sum and certainly than that median test. So if we can somehow show that indeed the assumptions are fulfilled, then by far the t-test is more appropriate than the other 2 that we could use. that is something that we will see quite a few times more. So this is the general thing that we could have here. We have all kinds of tests and models and statistical things we can do, and that we're only allowed to do if certain assumptions are fulfilled. We'll see more of those. So let's take this example here. Okay, test 1 assumes that assumption 1, 2, 3, and so on is true in the data. And if they are fulfilled, you can estimate something. And the example that we had was t-test, but you could think of many others a couple of weeks down the line. And we have a test 2 that has no assumptions whatsoever. In this case, it would rank some median. And then, typically, all the time, what you will have is, if all of these are fulfilled, then test 1 is for sure the better test, by a wide margin. So the testing of these assumptions is quite important and is an integral part of many of these statistical tests, and also a bit of a nuisance. A lot of the work that you want to do with the data is something where you do the actual statistical test that will lead you to an answer, and not so much the, but was I really allowed to do this? And, but nevertheless, you have to do it, and it makes quite a bit of difference. Okay, now, drilling this in one more time, for all tests that we've now seen, and we've seen quite a few already, we have something where there is an H0, and the H0 involves inequality, otherwise we cannot calculate anything. Not only we, but also statisticians cannot. Then we come up with a test statistic, something, a number of which we know the distribution. And in some cases, well, very few cases, we can come up with that number ourselves, for instance, when we're flipping a coin. But quite fast we are sort of out of steam there, and we have to get the help of a statistician who thought of this before. We saw this for a chi-squared example, and we saw it for a testing normality. We have people who did this already, and these numbers are integrated in statistical software as Stata. Then what you do is, okay, if H0 is true, if indeed we have a normal distribution, if indeed we have the same table here than we have there, then what are we expecting to see here? We get the test statistic. The test statistic is, 83.5, and because we know the distribution, we're able to figure out, okay, is that a weird value to get here, or is it something that we could have expected given H0? Okay, so we have the coin flip in the beginning. We have n by m tables that gives us a chi-squared, or sometimes a Fisher's exact. We have normality testing before running a t-test. We have a t-test, we have a ransom test, we have a median test. All these are the same, and all the rest that we're going to see follow that same recipe. All right, that leaves just a couple things left here. One thing is something that is a bit more intuitive than what we saw before in the n by m table case. If you find an effect there, if you find, okay, the independence of the rows and the columns is indeed violated in this case, then we could come up with an effect size that was called Kramer's V, and we have something similar here. Here it's a bit easier actually. If you have a normal distribution over there and a normal distribution over there, and you look at this difference, and you find, yes, I think there really is a statistically significant difference, then how large is it? Well, you could just argue, yeah, how large is it? It's this large. One's here and the other one's there. But I'd like to be able to say something about the effect size that I can say for all kinds of analyses that I run, and that is, so to speak, portable across different analyses. So if you are testing something on your data, and I have a totally different data set, and I'm also testing something with a t-test, and you are saying, okay, I have an effect size of 0.3, and I have an effect size of 0.6, I want to be able to say, okay, mine is really bigger than yours, the 0.6 is bigger than 0.3, and makes it a larger effect that I found. And the way to do it is like this. The easiest would be to look at this one first. Cohen is the guy who came up with it. It's called Cohen's D. And what it does is it looks at first the difference between the mean for the one group and the mean for the other group, so that indeed is that difference between the two humps that I talked about. And it divides this by S. We saw that S before. That's the standard deviation. So that is how wide that hump is. And if we assume, as we let's say normally do, that not only both of these are normally distributed, but they also have the same width, then this is just a single number. It becomes more complicated if we have one that is quite small in terms of the standard deviation, and one that is really big in terms of standard deviation. Then that formula becomes a little bit more complicated. So, that will work too, but it's now slightly different. But the idea is to look at how large the difference is between the two normal distributions compared to how wide they are. And that is the standard definition of effect size for these kind of things. Yeah.
Yeah, if you try to determine Cohen's d in Stata, you always assume unequal in Stata, right? Which you just saw in the first hour. The Stata then automatically also assumes unequal variances for the Cohen's d, and therefore this is the second one, or do we have to put something else in?
Stata by definition uses this one. And Stata will find out, so to speak, that it's actually that one if the group sizes are equal and the standard deviations are equal. But Stata has to figure out what the standard deviation is for these separate samples, for the one and for the other, and we'll do it. So Stata will simply take into account any difference if they are there. Yes?
How large does the value need to be for it to be a large effect?
Yeah, that's on one of the next slides, I think. Good question. First, before I forget, here from this you can simply see this thing is always positive. So this one could be positive and negative. And in principle, it doesn't mean a thing because you can always order these in such a way that the bigger one is the first one, so that this one is indeed a positive number. So even though you could get a negative number over here, it is standard to report about this only in terms of how far away it is from zero. So if you find a minus there, you can simply think it away, so to speak. And this is what we're sort of used to. The small effect is a Cohen's d of about 0.2. The medium-sized effect is a Cohen's d of about 0.5. And the large effect is about 0.8. And obviously anything that's larger than that is even bigger. Stata will have quite a few, not only Stata, quite a few other measures of effect size that we won't go into, such as hedges, G, and glosses, delta, and some of these you sort of get for free when you ask for the Cohen's d. Yeah?
Would an effect size of 0.499 still be small, or is that medium?
Yeah, that's exactly the kind. So the question is, if you have 0.49 for effect size, then what should we call it? And that's exactly the kind of debate you don't want to get into in statistics. For 0.49, this is about a medium-sized effect. Okay. Even these 0.2, 0.5, 0.8 are just, what we're used to. So we don't bother so much about the actual order of it. Okay. So let's see. Here one example that I found. I forgot to type unequal once again. Not good for me. I didn't check any normality here. I just wanted to give you an example of what the t-test itself looked like. And I was trying to find one where I indeed have an effect over there. See, this value over there is below 0.05. So here we see that H0 is actually rejected in this example. And the way to get the Cohen's d is by typing E size for effect size. And then from the effect sizes, the one about 2 samples, which is where you need to type 2 sample, and then you type the actual variables that you need, as income by female. That is what I checked in the data. And then you get your Cohen's d, in this case is 0.5, which is a medium-sized effect. Given that the sample size wasn't that big, you see that the confidence interval that you also get for Cohen's d is quite wide. So if you want to do a test of the kind, I find 0.51 here for that effect size, but could it have been 0.2 actually? Then indeed you would say, well, that hypothesis I cannot reject because 0.2 is in the confidence interval. That confidence interval would be way smaller if, let's say, the sample size would be 10 times bigger. Yes?
Say the output of the t-test is very, very low probability.
Yeah, so we're supporting H0, we're not rejecting H0, yeah? Or is that not what you mean?
Yeah, so the outcome of the t-test says very strongly there is a difference between.
Yeah, well, we have here. This is 0.0021.
Yeah,
So this
right.
is, yeah?
Doesn't that very low number say something about the effect size? Because I felt like if it's very, very low, it says that there's a very large difference, or is it just?
No, not completely. I can see why you would think that, but the other thing that it is related to is sample size. really big sample size, so 10,000 boys and 10,000 girls here, then even the smallest difference between the groups would in the end be significant, and even very significant. So then you can have a 5.1 in the one group and 5.11 in the other, which is, for all practical purposes, the same. But if our sample size is really large, then still we get a significant value over there. Okay, so this is the Cohen's d that you get here. Apparently, in this case, this is quite a large, a medium-sized, I should say, effect. Okay, that is for t-tests where we are comparing two groups where the groups are separate in the data. And we have a couple of other ways to do the same kind of testing, all of which are, let's say, versions of the t-test command, but slightly different. Given what we did already, this is relatively easy. So let's see how that works. First, a one-sample test of a mean. That could also help. So instead of comparing two normal distributions with each other, what we could try to do is simply look at one normal distribution and test whether or not the mean of the distribution equals a given number. For instance, here we have a variable labeled happy again. The mean is 1.22. And let's say that I want to test whether or not that mean equals 1.5. So H0 would be, really, the mean is 1.5, but nevertheless we get data that look like this. Could that happen? Or how likely it is that that would happen? The difference with the other test is that now we have to test for normality on the whole variable. So we had happy if happy baby equal to 0 and if happy baby equal to 1 because we had two groups. If we have the whole group, then we have to test for normality on that variable as a whole. And in fact, if you would do it, then you would see that normality in fact is rejected. And I didn't want to bother to find another variable to do the example on. So let's suppose that it wasn't and continue just as is. Then the command would simply be t-test and then happy equal to 1.5. And what you get is pretty much the same sort of output where you first see, okay, that was the mean of happy as we had it. And the actual test there in the middle here, 0.000, nothing, way below 0.05. So here I reject that H0, where H0 was the mean in the population is 1.5. Yeah.
Is it still relevant to this unequal behind
Say that again?
Do you still have to type into the command unequal behind the
No, there is no. There is no unequal here. Also, it cannot be because the unequal came from, if you have two normal distributions, is this width equal to that one? But there is no that one now, we just look at the group as a whole. Yeah.
Why don't you use t-test happy? Why don't you use the double equality sign over there?
Yeah, the double equalities, the equal 0 and equal 1 that you see, you only use those in conditional statements, if a variable equal to. And you could try to memorize this by reading these double equals as is in value equal to. Because you could interpret, if I have a variable and I say variable equal to 1, you could interpret this as the whole variable is equal to 1. 1 everywhere, a long column of 1. And that's not what you mean. You mean only the cases where the variable equals the value of 1. And yeah, that we do in the if statements that you put behind certain commands. But it's confusing, I totally agree. Other questions about this? Otherwise, we switch to the second example that is slightly different. Oh, and I forgot one thing. Because we could have seen this coming a mile away by another command here. That's CI, you saw that before. CI stood for confidence interval. Confidence interval means, and then you type the variable, in this case happy, and that will give you the basics of that variable as you saw before, exactly as you see there. But now with a confidence interval that goes with that variable. And here you can see, well, what's the confidence interval again? The values that you find in that interval, for all these, you would actually support H0. So that would mean if I would have had 1.3 there, that's actually inside that interval. There, I would not reject H0. I would have had 1.2 there, also in the interval. I wouldn't reject H0. So here, if I would check this this, I would immediately see, well, 1.5 is outside this interval, so for this, I need to reject any 0. Yeah.
And why would you even bother doing the ttest happy 1.5 to just type CI thing?
Okay, so let's say, try to come up with a practical example. We know that general happiness scores for employees of the university are on average 1. And now we do something, we try to influence them by giving them a life that is better for them. The idea is they get happier afterwards. So we measure them again. We get the distribution, not everybody is equally happy, but we do claim that we can really make a difference here and we can get the mean of that happiness at least equal to 1.5. So now on a test, how likely is it that the distribution that I have comes from a distribution with a mean of 1.5?
Couldn't you just type then CI thing?
Yeah, both will work. So I'm not suggesting that you necessarily do this. If you would do that, it would be fine too. I'm just using this because this is one of the other standard ways in which you use the ttest command. And I have that because that works as well. Yeah.
Wouldn't it be better if you want to write a paper to do the t-test? Because then you can say, oh, the chance is only this big. You reject it.
No, not really. Here, when you have the confidence interval, of course you have the same kinds of statements of, for instance, 1.5. There I reject it because it is outside the interval. And yeah, let's say the substantive interpretation, how likely is it? Yeah, you don't see that really there, and you also don't really see it here. One thing would be, for instance, what is halfway this interval, 1.22, the actual mean. Okay, there you totally do not reject H0. But in a way, in statistics, there is no totally not. There is, you just reject or you don't. And that's, in a way, the only thing that you need to worry about here. So in this case, if you report it like that or report it like this, none of that would make a big difference, I would think. So here you would see if you have 1.3 that you want to test, it's really on the edge, and you would see it from the confidence interval, or you would see it from that number over there because it would be very close to 0.05. So it doesn't make much of a difference. Okay, and one other example that is slightly different in its setup. Here you once again see the heart rate data, and there you could argue you could do a t-test as well. One was the control condition. I measure your heart rate in a standard situation. You are not thinking about anything in particular. And the other one is I measure you again. Now we are reliving an angry memory, and I also measure your heart rate over there. This is slightly different from what we had before, because now I know that I have two variables next to each other. And these two, the 60 and the 72, are actually from the same person. And that makes it slightly different. As I had it before with the happy variable, I had one long variable, and then another variable next to it that said 0, 0, 1, 1, 0, 0, 1, 1. So the two groups were beneath each other. Here we have the two groups next to each other. And the test, as you can imagine, is also perhaps even better, because here you know that this 72 belongs to that 60. The person here, with all of their quirks that they have, well, you have that there too. So here a person is in her own control. So if you would have, let's say, a hugely high heartbeat, 140 in rest, I hope not, but and then you find here, now it is 135. You know, that is a bit of a weird finding, because I know that you are 140 already when you're thinking about nothing in particular. So I'm controlling for you in a way, which makes the test, on average, stronger. Not always, but most of the time. How does that work in the data? First of all, in the data it looks now different. We now have the two groups next to each other instead of beneath each other, so that the command cannot be exactly the same. This is the data from Daniel. Here you see the heart rate in the baseline condition, the graph of that, and there the heart rate in the anger condition. And if you look at the summary statements, then you see that baseline has on average, let's say, 65 heartbeats per minute, and angry has on average 72 heartbeats per minute, which is slightly higher. And again, the question is, of course, is this statistically significantly higher, or could that be just a quirk? Let's see, do we have normality in these separate groups? Well, I just used the SK test in this case. We have a value here, 0.06, so just above 0.05, and here is 0.12, also above 0.05. So we're not rejecting normality, we're good to go here. And I'm testing now with the t-test, but slightly differently. I type t-test, and then baseline equal to angle heart. Baseline is one variable in the data, angle heart is another variable in the data. That is where the comparisons should run. And I see indeed the means here, 65, 72, and again over there, the actual test, 0.000 nothing, way below 0.05. So here we reject H0, and H0 was both of these variables have equal means, and apparently they don't, showing that there indeed is a difference in the data. Yeah. Okay, again, yes.
So why don't you use the double equal now? Instead of baseline equal.
These doubles we only use for if statements. So if you have a conditional on something, test this is equal to that, or test something, and then if, then you want to say some variable is in value equal to 3 or 4 or is larger than, then you get these double signs. Okay, if you really get into the nitty-gritty here, you could think about if it would be possible here to add that unequal again. And why isn't there any discussion now about that whole unequal part? Because we again have two distributions, one in one variable and one in the next. And shouldn't we compare that? Well, actually that's not the way it works behind the scenes, which makes it slightly more complicated. What's actually going on is what is being created is a variable that's equal to the difference of the two. And all the statistics is being done on the difference of these two variables. That causes that, in effect, we're only testing one variable here, and that causes that there isn't any unequal variances. For that, you need at least two variables, you have only one. So none of that is actually happening here in a one-sampled or in a paired test. Now let's see, in the paper of Daniel also thought that this would came out. Let's see. This is a direct copy from the paper. Heart rate was higher while recalling anger, mean equal to 70.06, and happiness, mean equal to 69, which is more or less the same what we had, give or take one or two cases, I think. Let's see. Where do we have this? Yeah, there we have the t-test, the value that was found, the p-value that was found smaller than 0.001, and then something that we didn't consider just yet. This is eta squared. This is another way of defining effect size that Daniel is particularly fond of. We could have used Cohen's d here as well. But normally this is the way in which you report about these kind of things. You say, okay, I find a difference here. The mean in this group is that. The mean in that group is something else. And I find two things, a test statistic, 7.11, and in this case, a p-value, and that was so small, 0.0000, we only saw, so what we report is smaller than 0.001, and that's pretty much it. Yeah.
Yeah, what conclusion could you draw in real life from the effect size?
The conclusion you want to draw there is, first of all, what is the size of the effect here? Is that something minute, where you could argue about whether or not this is interesting at all? Is this something that is a huge effect, where it's weird that we haven't found this before? So it gives you a sort of a feeling for how important the whole thing is. Yeah.
Yeah, but can't you find it in comparing the means?
Yeah, well, sometimes. Let me give you one example where this would work. If you do survey statistics, so you ask people surveys and you work on that, then very often you don't look at effect size so much. You, for instance, try to figure out, let's see, if people get older, then do they generally get happier? For instance, if you're interested in that. And then simply looking at, if you would find something there, well, as you get older, from 20 to 60, you get happier, well, loosely from the beginning of the scale to the end. And that in itself, without doing any Cohen's who knows what, is already saying something. However, this is not so obvious anymore if you have measurements where both of the variables are not so obvious to interpret. Here you see first, okay, the comparison is between the base condition and where you recollect something where you were angry, which is not that obvious in real life because normally you don't make that comparison. And then you measure heart rates, and there you also need to have an idea about, what are the general differences in heart rate that you get. If the general differences already are plus or minus 20, then the increase of 7 is not so much. But if the general differences are, let's say, 2 or 3 beats per minute, and now you get 12.5, this is a lot. And these effect sizes give you a standard way to deal with that. That's roughly the idea behind it. Other questions about this stuff? Okay, so this is all, let's say, the basic stuff where we do not do much else than compare two variables where at least one of the two, and sometimes two, are categorical. And for categorical, we have now, first of all, the complete command over there through that chi-squared or Fisher's exact. And we have more or less the same thing when we have something that is categorical with two categories comparing interval scaled variables. And we have a couple of variants of that. These all have the same kind of interpretation and the same kind of scheme that you need to get used to. And the rest is basically that you have to do it in Stata. When I was here on Wednesday on hours 7 and 8, you see people struggle every once in a while with, I know what I want to get, but it's not working. How is that working? That if statement, where do I need to put the comma? If I put two commas right after each other, does that work? And all that is simply practice time. You have to put in some hours just to get accustomed to these kind of things, and you should get the feeling as soon as you get one of these BPs, t-test on these variables, easy. The same thing over and over again, and you shouldn't need to think about all that. Otherwise, at the exam, it's going to work against you. Part of it is that you have to be able to be fast enough in doing this, not having to type a command and then check, again an error. Now, what's the error? The comma should be there. You have to get rid of that. And the only way to do it is through this. You have to do it, and that'll help. Okay, one example where I show it, hoping that by now this should be relatively easy. So this is one example. On old data, by the way, we have the same stuff in our data this year. So here we have estimated net incomes at age 35 by, not you, but the people before you. And we see here that for males the estimate is 4,500, and for females the estimate is 3,500. Okay, you can think for a while why that would be, because this difference looks quite substantial. Here we see it once again. First of all, that the differences are, if you look at it in more detail, basically like this, and to a large extent caused by 8 guys who think they are going to make a major amount of money. And they might be right, who knows. But I think that the bulk of the differences come from this. So let's see, what would I do here? I test normality, swilk, estimated income for boys, that's there, and for girls. Okay, violated. So I need not even do that SK test anymore. This one already doesn't work, so for sure this is certainly not a normal distribution. Any kind of transformation, might that work? Okay, I tried the ladder command, ladder estimated income for boys, ladder estimated income for girls, and now I'm trying to find one where here in the right column you have values above 0.05, and where I find a row both here and there. The same one actually, where this would work, and we get one, the inverse, 0.836, there's above 0.05, and 0.82, so there it works as well. So I'm now creating a new one, 1 over estimated income. And from that, I know if I do the normality test there, that is likely to work. Yep.
Can you also skip the results of the Shapiro work test with the ladder command and see if there is a positive chi-squared variation for either of them? Because then also just the regular items again.
Yeah, in principle, I would be tempted to say yes. The only thing is that here you only get the SK test actually, and that swilk test, which is in a way the stronger one, is not in there. So this is why I typically start with that swilk test to begin with, and see if I can do this from there. Okay, so I create a new one, 1 over estimated income, and now I can run my t-test. T-test 1 over estimated income by female, assuming unequal variances. This time I didn't forget. And here you see, yes, 0.0007, way below 0.05. So we are rejecting here that the mean of the boys equals that of the girls. And I can double check even with the other two tests. I didn't need those, but again, nevertheless, on the original x-equal variable, do that median test. Again, I find the difference both here and there. And I find the difference in the rank sum test. So, you know, whatever kind of test you throw at it, there apparently is a difference between the boys and the girls. And as you can see, you know, as soon as you know what to type here, you should be done in a couple of minutes with one of these analyses. There are a couple of those in the wikis. Every once in a while, I try to make sure that you have to do something with the data before actually doing something with the variables, because that might complicate matters at least a little bit. But in principle, this is all there is to it. Any questions about this? If not, then a slight word about the test that's coming up on December 7th. That's on a Wednesday on hours 5 and 6. The material for that test will be all the material that we have completed the Wednesday before. So that will give you a week to let it all settle in. And the test itself, you won't be able to use Stata. It's all stuff that you have to answer inside the browser. What you will get is most, perhaps even all, multiple choice questions. The ones that are not multiple choice will be short answer questions, so nothing where you have to run Stata and do a lot, but simply something where you can answer with a number or do a sentence and that should be it. Anything else that I need to say about that? No. Yeah?
You said we aren't allowed to use data?
No.
So how do we do that?
Well, first of all, I give you questions where you don't need Stata to give me an answer. That would be one. And what I will try to do is make sure that, for instance, I show you output from Stata and I ask you to interpret.
Okay.
Or